Have you ever been walking around on a carpet when all of a sudden you felt a zap between your fingers and the nearest metal object? The zap you felt is composed of a charge called static electricity. Static electricity is generated when two conductive surfaces are rubbed against each other. The force between the two objects causes the atom's particles to become charged, strong enough to temporarily ionize the air around it. The charge that's generated from this can be either positive or negative and acts accordingly, similar to a magnet. Many people studied this charge, which led to many inventions involving it. One of the men that made invention was named Georg von Kleist in 1745. He invented the Leyden jar, which is a device capable of storing static electricity. Many other inventors studied his invention, such as Benjamin Franklin. All Leyden jars have something in common, even though they're all not exactly made the same way. All of them have an interconductor of some sort, which is usually tinfoil or water, and it also needs another separate device called an electrophorus to charge it. In my experiment, I had 4 problems. In my first problem, I asked if charging electrophorus using a balloon or acrylic sheet would cause a greater electrical output. My second problem asked if varying lengths between charging the jar and discharging the jar would also affect voltage output. And my third problem asked if adding fluid inside a jar would decrease voltage output. And my fourth problem asked if charging electrophorus longer would increase the voltage output. For my first problem, I hypothesized that the balloon would produce more charge than the acrylic sheet. And for my second problem, I hypothesized that the voltage would decrease as the time between charging and discharging the jar increased. I also hypothesized for the third problem that the water would decrease the charge and the pot would decrease it even more. And for the fourth problem, I hypothesized that charging the jar for longer would increase its voltage output. Before I could start my experiment, I first had to make an electrophorus in the Leyden jar. To make the electrophorus, I first taped a styrofoam cup to a pie pan, and then secure it with Scotch tape. And then to make the Leyden jar, I first made a hole in the lid of an empty film canister, and then pushed a bolt with a washer through the hole, and then placed a nut on the screw. I then cut some rectangles of foil and lined the outside and the inside of the jar with it. I then took aside some bronze wires, cut it into pieces, and sanded one end so I would be able to conduct electricity better. I then wrapped the sanded wire on the outside of the jar and covered it with electrical tape for safety measures. I then cut a separate insulated wire into 2 pieces and then separated each end so that I could secure one end to the lid of the jar and the other sticking out to gather electricity, which I'll demonstrate later. Take another bronze wire, I would then secure it to the bottom of the lid, making sure it only barely came in contact with the foil on the inside of the jar to accurately gather charge and remove it. With this, the Leyden jar is now complete. To charge the electrophorus and then charge the jar, I would first heat a rubber balloon on an acrylic sheet for 30 seconds, like this. When this was done, I would then use the electrophorus to transfer the charge to the jar, like this. I would then pick up the Leyden jar, hold it to the frayed end of the wire, hold it for 2 seconds, then remove the electrophorus. The jar should now be charged. I would then scoop the bronze wire hanging here towards the nail and discharge. I repeated this process 5 times for each of my problems so I could get accurate results. I then moved on to my variables so I could test each problem. For my first problem, I charged the jar like normal, and then for the second problem, I gathered the charge from the balloon instead of the acrylic sheet instead. To charge the balloon itself, I rubbed a separate wool cloth onto it for the same amount of time as before, so it could generate static on it. The constants for this portion was the time between charging and discharging the jar, the wires used in the interconductor, and the time waited between charging and discharging the jar. My variable was the charging method. For my second problem, I waited longer between charging and discharging the jar, starting with 15 seconds and then 30 seconds. I then I gathered the charge from the acrylic sheet because the balloon's charge seemed more unstable. For this portion of this problem, my constants were, just a second, my cards are all disorganized. My constants were the interconductor, the charging method, and the wires. My variable was the wait time. For the third portion of my experiment, I said that having some fluid in the jar would decrease electrical output. To test this theory, I added some water to the inside of the jar, and then repeated the same process. I then removed the water and replaced it with soda pop. We used Pepsi for this portion of the experiment, and then repeated the process once again. My constants for this were the wires used, the charge time, and the wires used. My variable was the inner conductor. For the fourth portion of the experiment, I charged the electrophorus for 60 seconds instead of the usual 30 seconds, and then repeated the process as usual. My constants for this time were the wires used, the inner conductor, and the wait time. My variable was the charge time. The results for my first portion of the experiment said the acrylic sheet had an average of 4,800 volts with a minimum of 3,000 volts and a maximum of 6,000 volts. The balloon, on the other hand, had an average of 6,000 volts with a minimum of 3,000 volts and a maximum of 9,000 volts. For my second problem, the immediate discharge had an average of 4,800 volts with a minimum of 3,000 and a maximum of 6,000 volts. 15-second delay had an average of 6,000 volts with a minimum of 3,000 and a maximum of 9,000 volts, while the 30-second delay had a 5,400 voltage average with a minimum of 3,000 volts and a maximum of 9,000 volts. For my third problem, which is the alternative additives and fluids, the normal aluminum foil had an average of 2,700 volts with a minimum of 1,500 and a maximum of 3,000 volts. The water had an average of 1,200 volts with a minimum of no volts with a maximum of 3,000 volts, while the Pepsi had an average of 600 volts with a minimum of 0 volts and a maximum of 1,500. For my 30-second charge time, my average was 4,800 volts with a minimum of 3,000 volts with a maximum of 6,000 volts. The 60-second charge time, however, also had 4,800 volts average with a 3,000 volt minimum and a 6,000 volts maximum. My hypothesis for the first problem was supported. However, the charges for the balloons seemed to be more unstable and unpredictable than the acrylic sheet, so we used the acrylic sheet for the rest of the experiments. In my second problem, my hypothesis was not supported because it appeared at the 15-second charge time the charge actually increased. After that point, it went on a steady decline as shown by the 30 seconds decrease. In my third problem, my hypothesis was supported. The normal aluminum foil performed better in the water, which performed better than the Pepsi. In my fourth problem, my hypothesis was not initially supported. The 30 and 60-second charge times results were exactly the same. This might be because the jar is only a certain size, can only hold so much static. If you had a larger jar, you might be able to see a more noticeable difference, but because of my experiment, we were not able to. Are there any questions?
Did you run into any problems doing this project?
Yes, when we started this experiment, we actually built the jar entirely different. We had the inside made with water and the outside was in tin foil, but instead of the wires, we just had one long nail. We tried to do this experiment by measuring it by moving it closely to a metal sheet, but when we did this, the jar actually did not discharge, so we had to remodel our experiment.
So how did you measure the volts? You had a spark? Did you have to transfer this length of the spark to volts, or how did that work?
We first determined how long the spark was, usually in millimeters because of how our project worked. I then used a formula which was each centimeter was 30,000 volts, which our millimeters then was 3,000 volts, and we then calculated it from there.
Thank you.
Thank you.